Welcome to today's lecture. Today we will discuss about noise section. So noise mainly classified into two categories. So in noise analysis it is mainly classified into two categories: external noise and internal noise. So external noise classified into three: atmospheric, extraterrestrial, industrial. In extraterrestrial noise, it again classified into solar noise and cosmic noise. Okay, these comes under external noise. Okay, atmospheric noise means noise from surrounding atmosphere. Extraterrestrial means noise that is coming from solar, that is solar noise. Cosmic noise, that is noise coming from other galaxies. Okay, so next is industrial noises coming from the industrial area. So next is internal noise. So main classification: external noise and internal noise. So in your curriculum, BTech curriculum, they discussed about internal noise. Okay, so what are the internal noise and their classifications? So the first one is thermal noise, short noise, partition noise, flicker noise, and burst noise. Okay, these are the 5 different noises. First one is thermal noise. Okay, what is thermal noise? Thermal noise is also called white noise or Johnson noise. Okay, so by its name itself it is clear. Thermal means it depends upon the temperature. Okay, we know that materials are made up of atoms and molecules. As the temperature of the surrounding increases, this molecule gets some energy and they starts moving, and the motion is actually random. Okay, the noise generated with this random movement of molecules is called thermal noise. So what is thermal noise? Due to the rapid movement of a random motion of molecules or atoms, that is electrons or atoms inside the component. Okay, each component is made up of electrons or atoms, and these atoms or molecules moves in a material due to increase in temperature of the surrounding. So this random motion creates a noise. Okay, and that noise is called thermal noise. And it mainly depends upon the temperature. As the temperature increases, the random motion of molecule increases. This random motion of electrons in a resistor gives rise to electric current to flows through the resistor. For example, you take a resistor. Okay, a resistor is also made up of some material only. Okay, some resistor combination, we know what are the different combinations used to make resistors. So this material is actually made up of atoms and molecules. Okay, as the temperature, these resistors are definitely there in the electronic components. So a communication system made up of electronic components, and that components have resistors. As the temperature of the surrounding increases, these molecules or atoms or electrons in the resistor starts moving. Okay, so due to this increase in temperature, the molecules or atoms get some energy and it starts moving, and the movement is random. Due to this random movement, these are carriers, so this carriers random movement creates a current. Okay, so this current flows through this resistor only, and it creates a voltage across the resistor, and this voltage is called a noise voltage. Okay, this current is actually noise current. Why? Because of the external temperature, carriers are moving random. Okay, due to this random movement, a voltage is developed across the resistor, and this voltage is called noise voltage. Okay, so the power corresponding to this noise is called noise power, and noise power is proportional to T and B. Pn is the noise power. It is proportional to T and B. T is the temperature, T is called absolute temperature, and B is the bandwidth. You can make it equal sign. Pn is equal to a constant into Tb. Pn is equal to K into Tb. This K is nothing but Boltzmann's constant. Its value is 1.38 into 10 raised to minus 23 joule per Kelvin. So this is the noise power. Equivalent circuit of a resistor as a noise source. Okay, I told this resistor is made up of material, and it is also that means it is composed of atoms and molecules only, and these atoms and electrons, due to the increase in temperature, this resistance create a noise voltage. So that is analyzed here. Equivalent circuit of a resistor as a noise source. Okay, here I am taking, this is the resistor. Say noise voltage is developed in this resistor and it is represented by Vn. Okay, this is the resistor, and noise voltage developed across this resistor is represented by Vn. Okay, this is actually the equivalent circuit. This is our load. Okay, this is our actual load, RL. This is the resistance, noise resistance, and this is the noise voltage across this resistance. So it is modeled like this. We know that for RL is noiseless resistance. This RL is noiseless and it is receiving a maximum noise generated by R. Okay, this is actually noiseless resistance. This resistance receiving maximum noise power under the condition RL equal to R. See, if these two resistance are equal, we have a theorem, maximum power transfer theorem. Theorem says that when two resistance are equal, maximum power will be transferred from source to load. This is source resistance, this is load resistance, assumes like that. If these two resistance are equal, maximum power is transferred from the source to load. Here the power is nothing but noise power. So maximum noise is transferred to here if these two resistance are equal. We are assuming that condition. Okay. Now we will check what is the noise received at the load, or what is the noise at the system. So under this condition, maximum power transfer RL is equal to R. So noise power Vn, what is the noise power here? You know that power is equal to V square by R. Okay, so Pn is equal to V square by RL. Why? Because we need to find out the noise at here. So Pn is equal to V square by, this is the resistance, this is the voltage, power is equal to voltage square of voltage by resistance, V square by RL. We know what is V. V is Vn by 2. What is, how? This is the noise voltage. So this is the noise voltage, and that is the total voltage. We have two resistance, R and RL. This is R, this is RL. I need to find out voltage across this resistance. How to find out voltage across this resistance? Voltage division principle. Voltage across this resistor and these two are in series. So voltage across RL is total voltage into this resistance by total resistance. So total voltage across RL V is equal to total voltage Vn into RL, this resistance by total resistance. Here R and RL are equal, so RL equal to R, this is 2R, cancel out, so V is equal to Vn by 2. That's why I wrote, instead of V, Vn by 2, under the condition RL equal to R. Okay, so Vn by 2 the whole square by R, so Vn square by 4R. So from that, Vn square is equal to Pn into 4R, or Pn, we know that what is Pn, kTb. So Vn, instead of Pn we can write kTb. So noise voltage Vn is equal to root of 4R kTb. This is the noise voltage developed across this resistance. Next is short noise. This occurs in amplifying devices. Okay, amplifying devices, normally this short noise occurs. That means our amplifier, electrons and holes crosses the junction randomly and reaches at output electrode of amplifying devices randomly. See, these amplifying devices are mainly made up of semiconductor junctions. For example, a transistor have two junctions, emitter base junction, collector base junction. Okay, so electrons has to flow. Electron has to cross this emitter base and collector base junction. Then only it will reach the output electrode. Okay, so this junction crossing is actually random nature. Okay, so electron holes crosses the junction randomly and reaches at the output of amplifying devices randomly. This random movement creates a randomly varying noise. Due to this random movement, a randomly varying noise is created, and that noise is called short noise. Okay, short noise. It has uniform power spectral density. Okay, it has uniform power spectral density. Power spectral density is actually a graph. Okay, a lot of things we can find out from that graph. So it has uniform power spectral density for a diode. Noise current or short noise current is represented as IN is equal to root of 2 IPEB. Okay, IN is equal to root of IPEB, and IN is short noise current in RMS. IP is direct diode current. Is the charge of electron 1.6 into 10 raised to minus 19 coulomb. B is the bandwidth of the system. And this short noise is inversely proportional to transconductance and directly proportional to output current. Okay, so this short noise is actually directly proportional to transconductance and inversely proportional to transconductance, directly proportional to output current. That's about short noise. And short noise occurs in amplifying devices, and it is actually the random movement of electrons and holes at the junction create this noise. Next is partition noise. When current enters into a junction, it is divided into two or more parts. Due to this, a noise is generated called a partition noise. That means partition means when current enters into a junction, definitely it is divided into two or three. Okay, for example, consider a transistor. It is actually a junction. So this is the collector, base, emitter. Current flows through collector, it is IC. Current in base is IB. This is IE. We know that IE equal to IB plus IC. Okay, current entering into this, two currents are entering, one is leaving. So current entering into the junction is equal to current leaving. So there is a partition. Okay, current enters into a junction and it is moved to another junction. So due to this partition, it creates a noise, a small noise, and that noise is called a partition noise. And this noise is more in transistor than diode. Consider a diode, there is only one junction. Current entering here, this is the current entering, and here is the current leaving. Both current are almost equal only. Okay, it is like a closed switch, current entering and it is leaving. Okay, it is like a closed switch. So current entering and it is leaving, same current, almost it is equal. But here there is a junction, and these two currents are added up and you will get a resultant current. So due to this junction, current will be partitioned into two. So due to this partition, a noise is generated, and this is called a partition noise. Next is flicker noise. This occurs at low frequency. So flicker noise is normally low frequency noise. It is inversely proportional to the frequency. It can be ignored above 500 Hz. That means this noise is normally occurs below 500. Above 500 Hz, this is very negligible. Proportional to emitter current and junction temperature. This is proportional to emitter current IE and the junction temperature. That means emitter base junction, collector base junction, this junction temperature depends on this flicker noise. It occurs because of fluctuations in current density. Due to the fluctuations in current density, this noise occurs. This noise produces a fluctuations in voltage and current. Okay, this flicker noise creates a fluctuation in the voltage current waveform, or creates a fluctuations in the voltage and current. It will change the conductivity of the material. At low frequency, if this noise occurs, it will change the conductivity of the material, that is flicker noise. Another is burst noise. It is also called popcorn noise or impulse noise or RTN, random telegraph noise. Okay, this is also called popcorn noise or impulse noise or RTN, random telegraph noise. This occurs due to the defects in the semiconductor junction. We know that semiconductor is made up of semiconductor. If it is a transistor or a diode, definitely there will be a PN junction. Okay, transistor have two junctions, diode have one junction. This defects occurs in the junction. Actually, this PN junction is made by diffusion process only. Two semiconductor p-type and n-type material diffused together, will get a PN junction. Due to this process, some defects occurs at this junction, and due to this defects in the junction, a noise is created. Okay, so this noise is called burst noise normally occurs in transistors, FET, all those devices. Due to the impurities in the junction, it creates a noise. Why? Because two p-type and n-type material and different diffusion processor have we made at the junction to create a FET or a semiconductor, FET or a transistor, PNP transistor or a FET. We have to do a lot of diffusion process to make a semiconductor into a transistor or a FET. For this during this process, defects occurs at the junction. Okay, due to this defects at the junction, it creates a noise, and that noise is called a burst noise. It is called a popcorn noise also. Okay, and impulse noise or RTN. It can occur in small fluctuations of time. It is occurs in a very small fluctuations of time. See, this is actually an example for a burst noise. Look at here. It occurs for a short duration, then there is no noise. After that also there is a short duration noise, like that it is going. And it is not a periodic, it is a non-periodic signal, or it is not periodic. Okay, look at here. There is a peak, and after some time there is no peak. After some time, for a time duration, no peaks. Okay, after some time a peak, like that. In some places the peaks are coming close to each other. Some places it is very far apart. So that is not a periodic waveform. Look at this waveform. This is also a burst noise. A peak is there, just beside there another peak. After some time there is no peak, like that it is going. But the thing is, here amplitude of all the peaks are equal. That is the condition. That is the things which we noticed here. So peaks are equal, but it is not a periodic. It is also a low frequency noise. Why it is called a popcorn noise? Means, suppose intentionally you are adding this burst noise to an amplifier, it will give a sound like a popcorn machine. Okay, the sound from a popcorn machine, it is like that only. If we put this waveform intentionally to an amplifier, it will give a popcorn noise at the loudspeaker. So that's why it is called a popcorn noise, and this noise normally occurs at low frequency noise. So that's about the noise classification.